Hello everybody, my name is Emanuele Bosoni and I'm going to present a few slides about the AiiDA-SIESTA package. AiiDA-SIESTA is a Python package whose aim is to facilitate high throughput simulation with the Siesta code. Before starting, I would like to acknowledge the many people that contributed to the project. First of all, we have Victor Manuel Garcia Suarez that started the development back in 2017. Then there is Paul Febrer that recently contributed some very useful workflows. And then there is myself and Vladimir Dikan that, under the supervision of Alberto Garcia, are in charge of the main development and maintenance of the code. As I said, AiiDA-SIESTA allows high throughput simulation with the Siesta code. In this slide, I want to cover the concept of high throughput, since many of you might not be familiar with it. In a very pragmatic way, we can say that high throughput comes from the idea that when high volume of data can be produced without much effort, it is convenient to calculate or measure properties of an entire category of choice and to analyze the data afterwards. The advantage of this approach is that from the data we can extract property correlation that can be used to guide the search for systems with ad hoc characteristics. In terms of computational material science, this translates to the fact that when a physical quantity can be calculated in a computationally convenient way, it is then convenient to study many materials at the same time and create a database of calculated material properties. Then this database can be navigated in search for materials with characteristics that are good for a particular application. This is the process that is sometimes called materials discovery, and it is getting very popular nowadays. So in a sentence, we can say that high throughput approach is actually this process to create a database of calculated material properties. This approach differs from the standard approach in computational material science, at least for 2 points. The first one is that the focus is now on the standardization of the calculation process, so the creation of what is called the workflow. And this differs from the standard approach because before, usually people tailor the method to the system they have to study. The second point is that here in the high throughput, the attention must be given to the data organization, since most of the science is done a posteriori during the data analysis. For these 2 points and many more reasons, it is convenient to have a dedicated computational infrastructure that helps you with all the aspects of the throughput. This computational infrastructure is AiiDA. So here I'm going to explain you the 4 pillars of the AiiDA project, and hopefully you will understand what AiiDA can do for you. So the first one is automation. This means that AiiDA can prepare, submit, and retrieve the results of a calculation in an automatic way. This also includes the submission to external computers, so to a remote cluster, for example. The second point is data. This means that all the data, and so the calculation and the input-output, are nodes in the database. So this is automatically done, and this ensures that we can keep track of the provenance of everything. Also connected to the data, we can say that AiiDA provides you with a query system that allows you to access the information on the data you produce in a very easy way. The third point, which is called environment, signifies that AiiDA gives you a very flexible platform where to encode the complex steps of the scientific workflows. So it does not support only the single calculation, but also you can encode different steps of the scientific workflow involving different codes. The fourth point is sharing, which is connecting to the queryability of the database. In fact, the data you query, you can also group them and export them and share them with as many users as you want. Now in this slide I want to cover again the basic concept that I just explained, but from a more computational point of view. And I hope this is gonna give you a feeling of how it is to work with AiiDA. I will not cover the setting up of the code and the external computer and so on. You can find all the information in the tutorials. Here I want just to cover the concept of the data types. So first of all, AiiDA gives you Python classing that are meant to host the data, and have the primary role to allow the storing in the database in a basically automatic way. So there are two types of these data types. The first one are simple wrapper of Python types. So for example, you see the example here of the float. And then you have more material science related object. For example, I give you here the structured data type, which is meant to host crystal structure information. This structured data allows the definition of the structure in many ways. You can, for example, use other Python packages, for example ACE or PyMagen. You can import from file, you can manually define everything, and so on. Moreover, Siesta data give you structured data gives you some tools, for example, to calculate the volume and so on. So on top of this role to allowing the storing in the database, these data types also can be seen as a first effort to the standardization of the description of physical quantities. In fact, we have to remember that AiiDA is meant to give you a same interface to do calculation with different codes. So, for example, in this case, to define in a unified way the structured data is already a step toward the standardization, the physical property. But there is more on that in the AiiDA community, and you can look at this project if you are interested. The second concept I want to cover is the one of the calculation plugins. Calculation plugins are the most important building block of the AiiDA ecosystem. In fact, they are the one that allow the connection between AiiDA and the database and external codes. So here in this 4 line, you see how easy it is to submit a calculation. So you have to import these classes, and then you have to call the calculation you want to do. So for example, for Siesta, this would be Siesta here. And then you can submit the calculation passing all the inputs. The inputs are defined through data types, and for the Siesta case you will have an example later. One important thing to say is that the plugins are not internal to AiiDA, but are supported from external packages. So for example, the Siesta calculation are supported through the AiiDA-SIESTA package. Finally, we have the workflow concept that I already explained you before. The submission of a workflow is very similar to any calculation, as you can see, but as I said before, the workflow is different in concept because it's meant to encode many steps involving many codes. So here I give you an idea of how it is to use AiiDA from a user perspective, but of course it is very interesting as well to see how to create your own workflow and to support your own codes. But for that I have to point you to the AiiDA tutorials. Just to finalize this first part about the AiiDA, here I just want to show you a pictorial representation of how the provenance is maintained in AiiDA. So as you can see, all the inputs are connected to the calculation and the outputs as well. And then I want to show you how easy it is to query the database. So for example, here I want to ask for the Siesta calculation that have a mesh cutoff of 800 Rieber, and this it's simply the 3 lines you need to do that, and then you can group this calculation and you can export them and to share them. I now go to the second part of my talk, where I'm gonna talk about the AiiDA-SIESTA package, which is basically the package that allows to run Siesta calculation through AiiDA. Here you have an overview of all the information you need. I'm not gonna do a tutorial now about that, so you can look at the documentation for that, but I'm just gonna cover a few capabilities and tools we provide in this package. First of all, I'm gonna show you again how to submit a Siesta calculation. We already seen that, but here we have a list of all the inputs that can be passed to the siesta calculation. I think they are mostly self-explanatory, but what again is important to say that these two inputs, parameters and bases, are simple Python dictionary just wrapped to the AiiDA data type, and they can accept directly siesta keyword. So this is important because allow full flexibility in running all the options of the siesta code. The only limitation we have in running siesta through AiiDA-SIESTA is that some quantity are not parsed, and the support for external processing tool is at the moment limited. So we now parse, so we store in the database the energies, the total spin, the relaxed structure, and the electronic bands. And also we support the PLSTM post-process code that is used to generate STM image from the local density of state. Soon we will support the density of state and the partial density of state. However, I can say that even with this limitation, it is always possible to retrieve entire file and post-process them locally. So you can define an extra input where you ask AiiDA to retrieve an entire file that is produced by Siesta, and then you have it stored fully in the database, and you can use the information there. So what I show you so far is just another way to run siesta calculation through AiiDA, and this just gives you the plus of keeping the provenance of what you do, and also to use the functionality of the AiiDA data type. So for example, the electronic bands are stored in a data type that allows you to plot the bands in a very easy way. However, in the AiiDA-SIESTA package, we also provide some useful tool for everyday research. The first tool I'm gonna present is called the Siesta-based workchain, which is something that had robustness in the running of Siesta calculation. In fact, it is a workchain that deals automatically with some common errors. So if we run a calculation and AiiDA finds out that there is a problem in the basis set specification, it's going to fix the problem automatically and send the new calculation. Another tool we have is called the convergence workflow that helps convergence test on Siesta parameter. You know that when we start the study of a new system, it is important to do convergence test. For example, test the mesh cutoff compared to the energy or the key-point mesh. Well, in AiiDA-SIESTA, we give you a tool that gives you a very easy interface to automatically do any type of convergence test. So, for example, here you can see we have the Siesta converger workflow, and you have to pass the inputs that are or what I described in the slide before, and then you have to pass this iterate over keyword where you specify the keyword you want to change inside Siesta, and the value you want to try out, and the target as well. So soon we're gonna also have a basis optimization workflow. Third tool I'm gonna present very quickly is that we offer some scientific workflow that help with some basic science. So here we have, for example, the band gap workchain, the equation of state workchain, and the Siesta STM workchain that creates STM images. Finally, we have what we call the protocol system. Protocol system is a system to get suggested inputs of workflow, and is available for all workflow and also for a standard Siesta calculation. So as I explained in the slide before, every time you want to submit either a workflow or a Siesta calculation, you have to define the inputs through the AiiDA data type. However, this can be a tedious process, and also is not very convenient when you are sure to use more or less the same input. So what we offer is a way to obtain inputs, so to call an input generator that generates inputs based on a structure, computational resources passed, and a string summarizing a choice of input. So this means that if you know that you have some set of inputs that are gonna work for the system you want to study, you can create a protocol where you list all these inputs, and then you can forget how to define the input in using data type, but just call this function. These are gonna return you something that is ready to be submitted. This field builder, the quantity that is returned, can be analyzed to see all the inputs, and also some inputs can be changed, so it gives you full flexibility in doing what you want. So this is a tool we think is useful for everyday research, but also we foresee that in the future we could provide protocols inside the package that could basically encode the expertise of the expert of the code. So this is a work in progress, and we hope to have update you on that very soon. This concludes already my talk. I hope I convinced you that AiiDA helps research with all the aspects of high throughput simulation with material science code, and it has a strong focus on preserving the provenance and facilitating the data access. In addition to the AiiDA capabilities, I show you that the AiiDA-SIESTA package offers some useful tools to help everyday research and facilitate repetitive tasks that are necessary when we use the SIESTA code. And with this, I concluded. Thanks a million.